This meeting is being recorded.
Okay, sorry, let me start again. So welcome back to the school. We are going to dedicate in this last lecture half an hour to give you an overview of the structure of the code so that you have a better feeling of where the different parts are. And with the help of the manual after the school, if you want to, and you want to keep on working with CosmoLattice, doing lattice simulations in general, you know in which parts you have to look in the code in order to implement your own physics. And then afterwards, we're going to do for another half an hour or so, a live discussion about the future of this field. Or actually, we're going to review a bit the history first, and then how things have been developed until now, and where we think we could go. What is the perspective? Therefore, let's start with Adrian, and then I will jump in with the discussion at the end. Please, Adrian, go ahead.
Great, yeah, thanks a lot. And yeah, please do interrupt this question, because otherwise it's going to be very boring and definitely not half an hour. So, so yeah, the idea was just kind of to show you live and sort of review how the files are separated in CosmoLattice, because it's quite a big library, many files, and many different levels of complexity. So how this works is that when you download the code from GitHub, you have this CosmoLattice folder, of course, and in there you already have like 3 subfolders, and the only one that really matters is this source folder. The dependency folder is for a bit more advanced usage, and also to install, for instance, FFTW3 directly. There is a script that can help you to do that. Probably you saw that when you're installing the code. But what really matters is this source folder that in itself is divided in a few other subfolders. The one, again, that will really matter is only the include, where all the library is situated, and the models that you already know, because that's where your models are. The test, you shouldn't worry too much about. This is really like for in the core library where I'm gonna get there this template before. Every file has basically a test file that goes with it, where the basic feature of whatever this file is doing is tested, and they are executed through this folder, but you shouldn't worry too much about it. Models, well, I guess I don't think I have too much to say because you played with it already. CMake is where some of the CMake features are coded separately in case you want to check what it's doing. If you have some bug at compilation, or if you're happy you know how to use CMake and you want to change some of the stuff, that's where you should go have a look. Then the main file of CosmoLattice, so the one that is actually compiled, is also at this level in the source folder, and this you may actually want to have a look. Maybe you already did. That's where really everything is put together. So the parameters are parsed, for instance. That's where, for instance, if the restarts happened or not, that's where it's specified. That's where it figures out whether, again, it should do the restart or it should do some initialization. That's where the evolvers, the measurers, and all of that are, that was not a good thing, are developed, are code. And that's where the simulation also is run for the number of time you want. And at the end, everything is saved if you want that everything should be saved. Otherwise, nothing is saved because you didn't say that you wanted to save everything. Then the really important subfolder is this include one, where really the whole library is situated. It's separated again into 2, which is kind of what we close this gray box, which is this Cosmo interface. That's really where all the physics, the cosmology, preheating physics, where you can do stuff out of the box, and that you learn to use this week is situated. And you have this template section that is more kind of the black box, where all the technical details that are coded and are not necessarily coded in a user-friendly way, but really sort of try to be efficient and maintainable. I'll probably start with the Cosmo interface because probably most of you, that's where you will want to do some tempering. If you want to change initial condition, change measurement, change evolver, or whatever, you will have to do it in this Cosmo interface subfolder. And then I will just walk you through some of the things in Templat that you may also want to play with. Some probably you will not touch because, yeah, it's too deep in the code, but there are still some features that are somehow apparent in Templat and that you can try to not so much modify, but maybe add to it. So let's go with the Cosmo interface. In there, you already have a bunch of files, and you have 4 subfolders that are kind of named in a way that should be sort of apparent what they are doing. In the files that are already at this level in the Cosmo interface, you have this abstract model file, which probably you don't really want to look at. So I'm still going to show it to you, but it's not something you want to necessarily modify. It's a class that basically implement the basic structure for models. And when you create your own models, it inherits. So it's basically gets everything that is coded in this class, all the basic properties. Your model will behave in the same way. And then whatever you implement in your model folder will be on top of this base abstract model. The Cosmo interface is just a file where all the files are listed for to include in some other places. The coupling manager, again, maybe you want to have a look. Probably you don't really want to modify it. Is simply where this coupling manager that you need to call for SU2 and U1 are defined. And it looks maybe overly complicated, but the reason it's coded like that is that it allows you to do some simplification during compilation. If the codes really know what couples to what, and it's encoded in this way in this coupling manager, the compiler can get rid of all the sectors that don't talk one to another. It can just discard any operation that is done there. Then we have the run parameters that is basically again a class that just stores all the basic parameters that you have in the input file that are always there. So dt and dx and all these kind of things. This is a useful file to know. I think if you want to check, for instance, for a while there was I think there is still a typo in the manual. One of the parameters is not called correctly. So if you have a doubt on the name of a parameter, you should open this file and you see that, for instance, here this outfn object contains the output file name, and you see that the name of the parameter is the output file. Data k-bin is a way of changing the binning of the spectrum, for instance. This is all explained in the manual, but if you have a doubt, you can come here. And if there is a parameter, you are like aficionados of CosmoLattice, you have 10 different models and you always add the same parameter, you could think of adding it here in your version also, for instance. The last slide there is this simulation manager, and this is also just kind of a convenient class that that mostly does the saving of the file to the lattice and the loading when you do the restart. So it's mostly for backing up the lattice that this class is used, and really does saving, loading, this backup function also, and it also creates some the information file, for instance. It doesn't do much more than that. The actual physics is really located in this other subfolder. So you have these 4 here. Definition is where we put everything that we didn't know where to put else, meaning really that are just definition of some physical law. Maybe I'm going to show them to you after. I first go in the evolver, initializers, and measurement. Evolvers, as the name suggests, is where the evolvers are coded. So there is again, a overheading evolver class that allows you to code that has coded some basic property of the evolver and allows you to switch between different evolver when you choose a different evolver in your parameter file. The actual physics and the actual evolver are coded in the files of the corresponding name. So here, for instance, there is this libfrag one. I think we already looked at it in my in one of the lecture I gave, and that's literally where libfrag is coded. Same for velocity verlet. Same for velocity verlet. And there is also some parameters that are defined here. And for instance, in the version that we haven't released here, there was also Rungekuta and the position verlet, and that's all in there. Another thing that is important is this subfolder in the evolver that is called kernels, and that's literally where the kernels are implemented. So for instance, the gravitational wave one, there is the Laplacian and the total energy, the energy momentum tensor for the gravitational waves. You have the one of the scale factors, and you have one for every field. So if you want to check what equation are implemented, or if you need to do some modification to the kernel because you do something a bit exotic, that's where the things are gonna be coded. For instance, in the version where we implement this non-minimal coupling, we had to go here and modify the scale factor and the scalar kernel because now it couples to the curvature. If you want to add a type of field also, you probably want to add some kernels here also. So, okay, questions so far, so I'll continue.
I see there's a hand up by Isaac.
Yeah, go ahead.
Yes, so I just have a quick technical question. I'm just wondering, so I see that you basically implement everything in the header files rather than having a separate .cpp. Is this correct?
Yes, exactly. Yeah, it's a header-only library. If you want, that means that you don't need the only thing that get compiled is the CosmoLattice.cpp. Yeah.
And so can I ask, why have you chosen not to have a separation between header files and implementation?
Well, it's like there are kind of two styles of doing it. This you can do it like purely header only, which is like that, or you can separate into CPP. It's mostly kind of a coding style. Both have advantages and disadvantages also in terms of compilation. The idea, I think, to do header only here was to have like less. It's kind of you often have less compilation errors when you do that. And also it forces you to have smaller files and kind of have a more, it forces you to have sort of smaller bits of function and smaller codes, which is also a coding style, but that allows you to maintain the thing more easily because everything is separated in small units.
Okay.
Meaning it's not exotic. If you want to, if you're interested in this kind of thing, you can even Google like header only versus not header only, and you will find a lot of people shouting at each other on Reddit probably. But
Okay. Thank you.
So the initializer is kind of same thing that the evolvers. Also, maybe something I should mention. Also, you see that for every of these files, there is a test file that comes with it, and it's empty. It doesn't do anything because in the Cosmo interface, we didn't really push this idea. This is also kind of a very good code practice. Is to do this this testing for every file that you write. So this is also, if you want to see a bit more, I think we had the file somewhere. Well, okay, you can ask me. I can send you some reference on actually like coding style and everything. This was really a vessel that kind of chose the style and and made me follow it, which was, I think, a really good exercise for me. But yeah, so these small test sections are, I will show them to you a bit more in the template things where they're really used here. They are not really used. We still have them because they are kind of tests for compilation also. You can see whether if you try to compile this test that doesn't do anything, whether just your syntax is correct or not. It just kind of useful to code initially, but nothing happened in the test in the Cosmo interface, but they are still there just like to check compilation mostly. In the initializer, you have basically one initializer for every type of field. So you have for the gauge field, you have for the SU2 gauge field, scale factor, scalar singlet, and all of that. And a lot of you ask questions about initial conditions. And so if you're serious about changing initial condition, that's where that's the file you will need to have a look at. So if we look at the scalar singlet, that's what is done here. And basically, we call some function which has this conjugate quotient fluctuation. And this is all implemented in this fluctuation generator, which basically call a bunch of different we implemented somewhere some random fields that are either uniform or Gaussian, and this function calls them according to the formula that are explained in the manual, and that gives the proper variance. I mean, all the things that you learned this week, they are coded in this fluctuation generator in a convenient way, and then they are applied to the scalar field in the scalar field initializer. And yes, so these are all the different initializer, and they are put together in this model initializer that basically the only thing it does is that it calls all the different initializer and compute the correct average that you need to initialize the scalar field, and also switch between expansion and whether you have background or not, and these kind of things. Then you have the measurement subfolder, and this, I guess you can guess that it does the measurement. Again, there is one measurer per type of field, and it literally just does the measurement. So for instance, this is the SU2. There is one function that creates some headers. So when you can switch on this option in CosmoLattice and verifies as a header, which is kind of useful when you want to go back to a simulation after some times. And then it literally computes, for instance, magnetic field, the electric field, so the norm of them, the Gauss laws, and then it add everything to some file with this add average function. So if you want to add some more measurement to the fields, you should go in this SU2 U1 scalar singlet measurer. And that's where the spectra is computed. Also, if you want to measure different combination of spectra, that's also where you probably want to change your things. And yeah, there is this occupation number, this gravitational wave spectrum, the energy snapshot. So this is this option that allows you to actually have a 3D representation of the different energies that you can turn on in the file. And yeah, that's basically it. If you have question about measurement, that's where you need to investigate a little bit. This measurement input-output, probably you don't want to have a look at it, except if you find a bug. That's where the measurement and spectrum are saved in the CosmoLattice format, and that's where also like the normal plain text thing is implemented, and where the binary HDF5 format is implemented for the spectrum. And for instance, if you really love HDF5 and you want to have that for the average, also you should probably implement it. That maybe we'll do it one day. Probably not, but yeah, you know. Okay, the last subfolder is this definition, and that's literally where, for instance, the matter currents are implemented. So this is the expression for the vector charge. So vector current for the U1 density and the SU2 density. So it's literally where you for instance, look at the scalar product of the doublet. So this expression implement psi bar gamma 5 sigma a. No, sorry, not gamma. I was working on fermion yesterday. I got confused. Just the psi dagger, the derivative, the pi dagger phi with the gamma the gamma matrix, this I sigma function here. Or for instance, you have the gauge derivative, the appropriately defined here. You have something that does this fixed background expansion where we coded the equation of state, some energies, so compute the kinetic gradient, electric, magnetic energy, and all of that in there that you need to call for the scale factor and all of this. So if you have a question about Gauss law, about Hubble constraint, about gravitational wave projector, you need to go check in this definition. That's basically what you need to do about the structure. Need to know about the structure of Cosmo interface. If you want to do some tweaking to the physics, it's all gonna be in there. And this is also summarized in the manual here. You have this tree structure that is explained, and yeah, you kind of need to go get a little bit familiar and know which phi is where. And that's probably what you may want to do if you start to use CosmoLattice more seriously. The part that you may never have a look at, except if you want to really do some tweaking, is this template part. And that's what I'm gonna go quickly through, but in less detail at the Cosmo interface now. Template is really inspired. I had to do some convincing, but it's because the way CosmoLattice is coded with this functional kind of the way you can basically type when you type a formula in CosmoLattice, is very similar to what would happen in Mathematica when you don't evaluate a function. It doesn't actually does the computation, but it just stores an expression. And the only time where things are computed is when you call some field is equal to some expression, and then it needs to compute everything and put it in the field, but it does it on the fly. And the way it's implemented is through what is called expression template in C++, and it used this template that you have in C++. So I thought it was fun to call that template. But yeah, since I need to explain the joke, it's not a very good joke, but I think it's quite funny, so still want to share it. So in this template, you have this different subfolder. FFT, well, I hope for you, you never have to go look what's in there. That's where we basically implement the fast Fourier transform, and it's implemented in a way that you can use different library to do the fast Fourier transform. So for instance, there is this FFTW, but there is this PFFT, and if one day PFFT breaks, we can implement another one in a simpler way. I see Antonino as a question.
Yes. Thank you for your presentation. I wanted to ask you, let's imagine, for example, a very simple simulation like the lambda phi to the fourth. Okay, I do the run command. Where is the routine which starts everything, and what does it in sequence?
It's in Cosmo. It's in the include. It's within the source folder. Is this CosmoLattice.cpp? Yeah? This is where the main is defined.
Okay, so this then calls all the other classes.
This calls everything in sequence, and you can reconstruct what's happening by going from this lattice if you want to look at the code yourself.
Okay, thank you.
I think Mohammad Hossein has another question in the chat, Adrian.
Yeah, sure. Can you? Yeah, what is it written? I became curious about 0CM. Oh yeah, that's funny. It's basically what is called so it's kind of a subtlety. Is if you want to do you can encode integer in a type instead of a variable. So meaning that you can create a different type for every integer. And that sounds kind of a stupid thing to do. But if you do that when you compile something, at the compilation level, when you store things in a variable, except for a specific variable, the compiler doesn't know the thing because it hasn't been initialized yet, and it can be whatever value. But if you know the value of the integer at compile time, a trick you can do is to store it in a type. And this is what this tag number, like tag 0, tag 1, tag 2, tag 3, that are used to label the equation of motion, for instance, are. And this 0 underscore c is a trick to basically declare a tag 0, tag 1, tag 2, tag 3. It's just a syntax sugar, if you want. That I stole from Boost, actually, which used this type literal, and this just basically a string that is then converted to a type by the compiler. Great. So in this templates, okay, for FFT, probably, hopefully, you don't need to have a look at it. Same for the parallel, except if you, for instance, want to port that to GPU, that would be great. Please tell us. Then you will have to modify there. Otherwise, that's where the MPI implementation is put there. At some points, we wanted to do some threading also, but we sort of gave up because it was not super useful. The parameters, that's where the parser is implemented, also probably not so useful. Yeah, if you wonder how, if you like the pastor, you want to use it, that you can extract it from there. Oh yeah, at some point to implement, yeah, there are some like hidden feature that we don't use so much, but there is, yeah, you can do some math in the input file, but probably you shouldn't. This session is something you don't want to know about also, so I'm not gonna say what it is. Util is really a whole bunch of random functions that do some like little things that are kind of nice. So there is one function that remove all space in the string. A lot of them come from Stack Overflow or from Boost or whatever, and we always reference it in the header of the file. This one probably, yeah, is a macro that ports something to strings. There are some like in older version of like before C++ 17, I think you couldn't do if at the level of compilation, so we had to implement it, and that's what this does, and all these kind of things. So it's just like a bunch of useful function. The only real place where you may want to have a look is in this lattice subfolder. That's where all the lattice, as a sense of like putting a field on the lattice and like play with it, is implemented. Memory is all the complication that comes from the fact that you don't need the same array to store something in Fourier space than in real space. When you do parallelization, you need extra memory, but not the same in real space than in Fourier space, and you need to move between these different representations. And that's where this is implemented, basically. Yeah, that's all what I want to say. Measuring tool, you may want to have a look sometimes. That's where the computation of the spectrum is implemented. That's probably something we need to improve at some point because it works well, but it's a bit hard to follow what is done, but that's where it is done. These loopers are where the iteration of the lattice is done. And yeah, that's where this is done. That's it. Input output is where saving the file to HDF5 is implemented for the backup. Ghost cells is related to parallelization. Field you may want to have a look at. That's where the actual field is implemented, and that's where we call the fact that when you have an expression, it's not evaluated, but then it's evaluated when you do the iteration. This is implemented in this field class. That's where the FFTW is automatically done also, because the field can be in configuration space or in Fourier space, and this is implemented at this level. And yeah, then there are a bunch of subclasses that helps you to do stuff with the field that are also there. And lastly, maybe also one of the useful things to know is this: when you go to this lattice, you have an algebra subfolder, and that's where all the algebra is implemented at the level of this expression a template. So, for instance, I don't know, if you want to compute, you have a weird potential and you want to compute, I don't know, hypergeometric function, let's say, or some combination of other function that has a name and that is not implemented and that should be useful for you. You can go and just do it here, meaning you go to algebra, and for instance, all the functions are implemented in this operator here. And for instance, we have addition, we have arc sinus hyperbolic. For instance, there is the arc sinus hyperbolic, but there is no the arc cosinus hyperbolic, and maybe you need to do it. So if you do need to do it, you go in this subfolder and you basically copy all of this, and you change the fact that this get function that tells you that at point I you need to return the value of the arc sinus hyperbolic at the point I, and you would just have to put arc cosinus hyperbolic here, and you would have a new function, and you'd be happy. Yeah, Antonino?
Yes, yeah, I have just a curiosity. For example, if I wanted to implement in CosmoLattice SU3, which file should I add and where?
Yeah, exactly. That's where I was getting at. So it's exactly, you asked the question exactly at the right moment. It's also in this algebra. So you have, this is all the scalar algebra in this operator, and now you have this subfolder that is called gauge algebra also. And in there, that's where the SU2 algebra, no, that's not true. It's not in the gauge algebra. It's in the, probably in the SU2 algebra. Yeah, there is a subfolder called SU2 algebra. And here, that's where all the SU2 algebra is implemented. So for instance, there is this class SU2 field that basically what it does is that it puts together, it takes three scalar fields, and it imposes the fact that it's an SU2 field, meaning that when you call the zero component of the SU2 field, it gets, it returns to one square root of 1 minus the sum of the square of the others, because you want it to be on the SU2 sphere. And then all the thing, for instance, the most complicated thing is probably the multiplication for SU3. Here, the SU2 multiplication is hard-coded at the level of the expression, and then there is another mechanism to make it more efficient also, and it's coded the second time. But that's where the multiplication is coded. So to answer your question, basically what you would have to do is kind of just yeah, it's a bit monkey work, but it's kind of painful. So that's why it's not done, because we didn't need it. But what you would have to do is to copy paste this folder, call it SU3 algebra, and then go basically phi by phi and modify. You don't want a doublet, but you want a triplet, and you want to change the I think if you go read the phi, it's kind of somehow, maybe you won't understand all the details, but the math that it's doing is kind of clear. So you can just go in there, and this is called complex field SU2 doublet multiply. So it's literally compute the matrix times yes, this computes like the multiplication of a complex field with the SU2 doublet. But if you want to look at, there is a file that does the multiplication of the SU2 matrix with the doublet also. So you just go inside this file and you change the doublet to triplet and SU2 to SU3, and you need to code the formulas basically.
Okay, what is the helpers folder inside the SU2 algebra?
Good question. Yeah, so this basically it's some it's a way to, so yeah, this is going a little bit in more details, but when you, basically you want to define you want to overload some operators sometimes to have like a clean syntax. So you can write, in this case, I'm looking at what complex field at SU2 doublet. I want to be able to literally, if I have a complex field and a SU2 doublet, I would like to be able to write complex field times SU2 doublet. So I'm overloading this operator here. But when you need to do that, the way the compiler knows that you have different, that it's not a multiplication between SU2 and something else, but it's just like a double times another double, is because for the SU2 doublet, they have this special function that is called SU2 doublet get. And that means that it's a SU2 doublet and that it has the algebra of SU2 doublet. So it has this function SU2 doublet get. Complex scalar field doesn't have this SU2 doublet get. And to define this this multiplication function, the compiler needs to know whether this specific operation dot is defined for the fields that it's trying to multiply now. And the way that you can do that in C++ is with this enable if type, which is some expression template, template function that basically could check whether the type R that you're trying to multiply has this complex field get method. And this as complex field get method that is implemented to be evaluated at the level of the template is defined in this helper. And basically all the different type of fields have their own as complex field get, as SU2 get, as SU2 doublet get. And all these things are basically defined in the helper.
So this helper is there because you are coding in C++, specifically, right?
Yeah, yeah, it's because it's coded using templates in C++, yes.
Okay, thank you.
Yeah, and so that's basically it. You have a few other algebras. So you have the complex field algebra somewhere. You have the spatial derivative folder is coded here also. So there is some optimized expression for the Laplacian, but otherwise it's literally just computing the backward derivative is the field minus shifting the field by 1 point in one direction. And here we see this tag thing again, because you know in which direction you want to shift. So you can encode that at compilation time. There is a random field generator that's coded there also. You have some algebra implemented at the level of arrays, so you can multiply arrays of field and it just like vectorize, so every field is multiplied separately. You have some global helper that do some C++ stuff also, basically. You have some constants that are implemented at the computation time also, so you can do some simplification. Yeah, and I think that's basically when you need to see. Probably if you do something, because even if you don't understand all the C++ stuff, you can, if you want to implement SU3, for instance, or if you want to implement different algebra, you can sort of do it by mimetism here, just by kind of copying the stuff and sending us a couple of email, I think. So yeah, that's, I think, basically what I wanted to say. I don't know if, Danny, you want to add some stuff about the structure of the code, but otherwise you can take it over.
No, I just want to highlight that, of course, thank you very much, Adrian, for this overview on the structure of the code. But I just want to highlight to everybody that at the end of the day, if you really want to obviously understand the structure and the contents inside of each of all the folders and files, well, you have to go through the manual and the code pretty much in detail. You know, I think with Adrian's overview in half an hour, you really have a good idea. And if you rewatch the video, this will help you to position it, to navigate yourself in the code. But at the end of the day, if you really want to go, you know, to do deep physics and to really control well the lattice, you need to do the work of going through the manual and the code in detail. That's unavoidable.
Yeah, but mostly the Cosmo interface. The thing at the end was really just to give you a flavor. But
mostly the Cosmo interface for those interested, of course, in cosmology application. But still, if somebody wants to add, certain functionalities, well, I mean, it depends on the level you want to use. At the end of the day,
yeah.
but let's say that the level you have acquired in this school is the most basic level, where you use essentially almost everything as a black box. You just learn how to modify, how to introduce a model of a scalar or a scalar charge under some gauge symmetry, how to put arbitrary potentials, and then run. But through deciding potential parameters, model parameters, or so on, lattice parameters in the input file. But even using it at that level, it requires some practice. Because you always need to understand your physics in first place, hence what are going to be your physical scales and the limitation of the lattice that you're going to have in order to capture that physics. And then if you want to do physics beyond that basic implementations, like for instance, the examples we were showing yesterday on non-minimal gravitational couplings, or today on axion coupling to FF dual, you really need to go into the structure of the code as Adrian is showing it today. Okay. But yeah.
Now, maybe a last point I wanted to make also is that yeah, so if you what is cool with the code that is not necessarily too hard when you're used to use it, about like see how you multiply field and all of that. If you want, you can also just use that to implement other stuff than this Cosmo interface. So if you want to solve some Langevin equation, for instance, and you want to do that efficiently, and you don't want to parallelize everything yourself, you can just use the fields that are already coded in CosmoLattice and use these classes to implement your Langevin solver, for instance. The cool stuff also about this template is that everything works in n dimension. So if you want to do some exotic or some like real-time dynamics, I don't know, from for some compactification of whatever in 4 dimension, or if you have a bulk dimension or whatever, you could also in principle implement that with CosmoLattice pretty easily because it's parallelized in n dimensions.
Okay, thanks. Are there any other questions about the structure? If not, we can also take them at the very end. Well, there is a question in the chat.
Yeah, I didn't get it. Someone is asking for the code in Python, but there is no code in Python. So
yeah, I'm not sure what you mean, David. Like, how do you want to generate the Python version of the code? All right.
I don't think.
Well, if you have questions, please, you can still ask them after the second part. Let's take 5 minutes break. I think we've been already around 45 minutes. Let's take 5 minutes. And then we reconvene and give the final overview discussion on the code, on the school, and the perspective of lattice cosmology as a discipline. See you now in 5 minutes. Maybe I can go sharing, Adrian. I think you have to stop sharing, sorry, and you are muted, by the way.
Yeah, sorry, I'm muted. Okay. I think I stopped sharing, right?
Yes, yes, yes.
Okay, good.
So I have to share through AirPlay. Let me see if this works.
Yeah, I may have to run a little bit before the end of your presentation, but if you have further questions, please don't hesitate to send me an email.
I have some difficulty to use my camera.
All right, I guess we can start. Now I don't see the control panel because I'm sharing. Can you confirm someone that you are hearing me?
Yep.
Yes.
Okay, excellent. Well, welcome back. Let's now finish the school with some brief discussion on the origin and especially on the perspectives of what I like to call Lattice-Cosmology, which I think is this discipline that we've been discussing in the school about how to lattice field theory problems, typically in 3+1 dimensions, corresponding to dynamics of the early universe, and then solve for the nonlinear dynamics at the classical level. Okay. So, well, first of all, just to tell you that despite the fact that, nowadays is, of course, becoming more and more common, the use of this technology, the history of using this kind of simulations is actually pretty old. And I think we can divide it in 3 decades. And it all starts, I would say, in the 90s, when the CMB, the first anisotropies of the cosmic microwave backgrounds, were being measured in 92 by Kobe, and in the late 90s, early 2000 by Boomerang and other experiments. In that moment, in the 90s, the resolution of the CMB anisotropies was not good enough to differentiate between 2 cases that could be behind the origin of the angular anisotropies, inflation and cosmic defects. So it turns out that actually it was in cosmic defects where I think the very first simulations of field theory were done. And this is really actually even back to the 80s, not only 90s. Of course, the capability of computers, first field theory simulation, sorry. The capabilities of the computer, of course, were very, very limited in that moment, but this prevented the fact that people could simulate in a rudimentary manner to mimic a phase transition and then the aftermath configuration of cosmic defects emerging. However, I think the field or the topic that really triggered the use of the lattice in a systematic manner or in a more systematic manner was inflation, but funny enough, not inflation itself directly, but rather post-inflationary physics. So following inflation, we know that we must reheat the universe. And it was in the late 90s. Have I started recording? Mohammed is asking. Am I not recording? I never stopped recording, sorry. Can anybody check if it's being recorded? Because I cannot.
Yeah, it's being recorded. It's recording.
Recorded, right? Okay, yeah, thanks. Thank you, Mohammed. Okay, after inflation, we need to reheat the universe, and it was precisely in the middle and late 90s where people discovered what is known as preheating. These are non-perturbative effects of particle production. Essentially, the fluctuations of fields into which you want to reheat the universe, they enjoy exponential instabilities. So they grow exponentially fast. This is the same as having occupation numbers much larger than 1. And then people realized that you could put this in a lattice. In particular, I think there were 2 seminal papers in '96 that put forward for the first time this program of lattice simulations. I have put these references in the chat. Let me just give you briefly the names here. One of these references is Prokopek and Moore and Ross, sorry, and Ross. If you want, I can write HEP pH 96 10 400. And the other reference was by Klevnikov and Kachov. And the archive reference number is HEP. Let me not copy this wrong. pH 96 03 370. So essentially, in these 2 papers, they realized that if you start from initial quantum fluctuations, since there's going to be these instabilities embedded in standard preheating scenarios like parametric resonance, occupation numbers then are going to grow exponentially as well, and hence it is justified to use these lattice simulations. Very good. That was really the beginning, but of course computers had not enough power to do very large simulations, but people realized of this possibility. And then in the very early 2000s, I think this is where the field really starts. Couple of authors made public a famous code in those times, in those years, which is called Lattice-CC. Okay, LE for in short. This was written by Gary Felder and Kachoff. And essentially what Lattice-CC could do, it could simulate a bunch of scalar fields. Let's label here with I. So it could simulate their Klein-Gordon dynamics. Let me erase here. Yep. Together with a self-consistent expansion of the universe. Namely, they were solving for the second Friedman equation, where the energy density and the pressure was expressed in terms of the kinetic gradient and potential terms of scalar fields. So this was, I think, the first time that this was systematically done and made public so people could use it. And as the name indicates of the code, Lattice-CC was really a code very easy to use and to learn, which could do this kind of dynamics, but it was always limited to this kind of dynamics. They were using leapfrog. As a matter of fact, for me personally, that's what I learned for the first time about leapfrog. And well, it was a powerful code, which was parallelized a few years after it was released. The parallelized version was called Cluster-Easy. And then, yeah, it became a powerful code, but limited to this kind of dynamics. Now, between 2000, well, let's say around 2010s, and this includes, years before, years after, it became clear that one could do much more. You could add gravitational waves into the dynamics of your scalar fields. You could add gauge fields. You only had to follow what Lattice-QCD people had done for so many years and just put it. This is precisely what we've been showing you in this school. You could actually put fermions as well, although this is, let me put it with a star here, extremely complicated and demanding. And this is why people have not carried on with this, because contrary to bosonic species, this requires lattices of n to the 6, which makes them essentially prohibitive. Okay, and you could put non-abelian interactions. Let me put it non-abelian gauge field represented by B. And people did that, including myself, my collaborators, and a bunch of other people. Now, the only problem is all of these were like particular implementations. In other words, they were private. We were modifying our own codes. We were creating our own codes, but we were never sharing them publicly. So people, if they wanted to imitate the physics or do their own physics, they had to write from scratch. Partially because it became clear that there was an interest by the community on this kind of simulations, and partially because it became clear to the people that we were doing these simulations that, there was a demand. Some authors started making, in this decade, around these times, slightly before 2010 and slightly afterwards, a bunch of codes public. Public codes but these were mostly on scalar fields. So essentially, these codes, for instance, we can cite H-Lattice, defrost, Gabe, just to mention few. These codes were like more evolved than Lattice-CC, but essentially they were mostly stuck with scalar field dynamics. In the case of H-Lattice, they implemented new integrators like the Verlet of higher order, but essentially they were still lacking of the kind of multi-varied type of fields that one may want to consider in order to take into account realistic cases. So finally, we get into the 2020s. This is when we release CosmoLattice. I mean, to be precise, we released it in 21, but in 20, we already put out our review on techniques. And we created CosmoLattice, realizing after many years of experience that it was clear that we had to separate the physics from the technicalities. And that's why actually CosmoLattice has those two main libraries separated. Okay, and the Cosmo interface is most likely what you want to touch if you just want to do new physics. Technicalities, again, it depends on your aim in order to understand how certain things work in the code. But as Adrian said, it might happen that you never want to touch that. No, it really depends how much you are of a computer geek or how much you are a theoretical physicist. No, where is the balance? Where is the point? It is clear that in terms of physics, there are many cases of interest that one can do. To mention just categories of this, there is inflation. Today we had a lecture about this. As a matter of fact, the results and techniques that Ander and Johannes were presenting are very recent. This gives you an idea of how long it took to develop all of this. The results of action inflation, nonlinear dynamics towards the end of inflation are from this year, literally. So inflation is pretty difficult to do because the exponential redshifting of scales, but on the other hand, it's doable. That's the point. Now you have a tool that if you learn to use properly, it's gonna allow you to do all kind of nonlinear inflationary models, or even nonlinear interactions in the linear regime when they are subleading. And this could help you to do non-Gaussianity, for instance. All kind of observable or aspects of inflation you can really, in principle, tackle, but what you cannot do is to follow the full 60 folds altogether. Okay, that's never gonna happen in any lattice simulation in 3D. So this shows you again that the lattice techniques, lattice cosmology techniques are very powerful, but always limited, you know, and you have to learn very well how to use them. Then, of course, the physics of preheating. This had been exploited since the late 90s. And of course, now with CosmoLattice, which is parallelized in multiple dimensions, and you can run it in literally thousands of cores, you could now run models where you can separate the scales much more, sample different coupling strengths that you couldn't do before, etc. So maybe it's not so innovative to use it for preheating, but it's certainly much more powerful given the technical capabilities that CosmoLattice provides. Then there is the very interesting case of cosmic defects. Cosmic defects in general, and strings in particular. This is really very interesting for the community of high energy physics and theoretical cosmology, because there is, on the one hand, well, action dark matter scenarios where you produce a bunch of cosmic strings under certain circumstances, global cosmic strings. And on the other hand, there is also the possibility of producing in grand unified theories local strings. And this code, these techniques as implemented in CosmoLattice, they are capable of dealing with this physics, but again, there is a limitation to how much you can separate the scales, so you have to use them with certain care. And you cannot do the full cosmic evolution of a network of cosmic strings. That's never going to happen, once again, in a lattice simulation. But you can still extract a lot of physics, which you cannot do otherwise, you know? So once again, it becomes fundamental to have at hand this kind of techniques. And finally, one case of particular interest to the community of particle physics is the ability to do with lattice simulations first-order phase transitions. This is particularly interesting because in the case of an electroweak phase transition embedded in beyond the standard model physics, this kind of the gravitational wave backgrounds associated to them can be observable at LISA, which is a major experiment foreseen in gravitational waves for the next decade, 2030s. It will be the first space-based gravitational wave detector. And because of this, there is a lot of interest because it's going to be an alternative way to probe particle physics. So essentially, you see all of this, you can do it with these lattice techniques, or as I like to call it, Lattice-Cosmology field. But of course, implementing the details of this well requires you to work. And the idea of CosmoLattice, this is where CosmoLattice enters into the game, is precisely to provide you a platform for you to implement this kind of physics. This platform is a complex platform. CosmoLattice is a complex code. It originated, you know, back in the 2014, 15, with my interactions with Paco, when Paco was doing the PhD with me. Then Wessel, who was a postdoc in parallel with me in that epoch, even though he wasn't maybe particularly interested in early universe, he was very interested in technical aspects. So let's say that Paco and I, we were very interested in physics. We were already discussing many cases, gravitational waves, fermions, gauge fields, scalars, other circumstances beyond that. And then we somehow got engaged with Wessel, who had a fantastic technical ability. And what we decided is to start designing a code together that, with certain advanced techniques of programming that Wessel put forward originally, would implement the physics that Paco and we were so familiar with. Now, it turns out that Wessel ended dropping from academia, but then we were very lucky to meet Adrian, who in that moment was doing his PhD with Shaposhnikov at IPFL. And Adrian actually is wonderful because not only he knows very, very well about this kind of technical aspects, as you may have noticed, but also he's very good at the physics. Let me choose this color, which means, you know, we could really connect Adrian with the physics sector here. And this was ideal, you know, because essentially Adrian took over on the templates that Wessel had prepared at the let's say, the infrastructure for the code, shape it furthermore, and then we started realizing all the program of physics that we've been telling you about during this week, all the scalar and gauge scalar theories in self-expanding backgrounds. Notice, as a matter of fact, that some of the algorithms and cases we have discussed, for instance, the non-abelian SU2 with self-consistent expansion, the algorithm we have presented in the lectures and that you can find in the manual and in our code is the only one. Written down, available in the literature. So CosmoLattice already contains some cases that have not been put forward before, but the most important thing for me is that besides the lectures and the theory, which is just the basic theory we've been telling you about during this school, you realize that if you learn those basic aspects of how to lattice field theory frameworks, and you see how this is implemented in CosmoLattice, then you are going to be able to start jumping into more complicated cases, such as phi square R, as we did with Ben and Toby. Unfortunately, Ben could not come to lecture this year, and that's why Nico took over in his lecture yesterday. Axial coupling, FF dual. This is what we've done with Ander and Johannes. And then, of course, there are other aspects that we are working on, you know, again, we haven't even told you about, but there is on the way now fluid dynamics. Plus MHD. This is going to be some work with Antonino and Alberto Roper-Paul. And other aspects. Now, the whole idea is that in the moment you understand the structure of CosmoLattice, you use it as a infrastructure, as a platform where you can implement literally whatever you want. This includes friction terms that people have been asking about, which actually would be rather easy, but this includes many other aspects, many other dynamics that you can think of. And as a final note, what I want to insist is that whether you want to play around with the physics that is already implemented, or you want to implement new physics, you always need to take into account that if I plot n, the number of points per dimension here, versus historic time, essentially in the 90s, people were doing lattices as pitiful as 8 to 32 points per dimension, which were already very costly. In the early 2000s, people jumped from 10 to 6 to 10 to 7. Then we started jumping in 2010s, you know, from 10 to 8, 2 to the 8, sorry, 2 to the 10. Okay, yeah, this is 1,000 points per dimension. And then in 2020s, we are certainly reaching now the level up to 8,000 cube. Okay, so if I plot this, literally it means a growth like this, you know. Now remember that n, it's roughly speaking the separation between your UV physics and your infrared physics. Separation of these scales. So this is about how much you are gonna get. Sorry, I realized I wrote 20. It's 2 to the 11, obviously. Let me write this. 2 to the 13. Okay, which roughly speaking is 8,000 points per dimension. Okay, so in the diagonal, we are gonna get close to, I think it's 14,000. That's how much we're going to be able to separate the scales, but probably we're not going to be able to do it much more because that requires already simulations of the order of 100,000 cores. So maybe it'll be really practical if eventually we jump into GPUs to gain some velocity. and power, but at the end we are going to be limited, you know. So when you want to do physics, you need to understand very well this limitation, this limited separation of scales, and you need to make sure that if you have a spectrum of certain physics you want to represent, for instance, gravitational wave spectrum versus frequency. You want to compute a stochastic background of gravitational waves that has certain features. You are not going to be able to separate this much more than 10 to the 3, 10 to the 4. You have to live with that, but that's a lot. And you can do a lot of things. So essentially, I would like to conclude this kind of perspective that I'm giving you here with my own opinion, which is in the near future, in the 1-2 decades to come, these kind of lattice cosmology techniques are going to play a very, very important role in making exact predictions for the early universe and for theoretical physics in high energy particle physics, for the simple reason that they can address non-linearities that you cannot address anymore otherwise. And hence, it is only through these techniques that you're going to be able to make precise predictions for instance, the gravitational wave background, from nonlinear aspects of inflation, from preheating, from cosmic defects, or from phase transitions. So, a matter of fact, in the case of phase transitions, in the last 10 years, the field is completely dominated by these lattice simulations. So, it is really up to you if you want to take this opportunity and build on the basic knowledge you have now, the basic view you have on the code, to go deeper inside. Again, with the help of the manual, I think it's going to be pretty much feasible. And then I'm pretty sure you'll be able to start implementing your own physics. There are a number of groups in Europe, mostly so far, that are implementing already their own scenarios, model physics with CosmoLattice. And you see, people are jumping into this kind of physics precisely because of the power it has. So I hope you appreciate the opportunity you've been given to follow for free this school online, so everybody could join. And well, now I think I want to conclude here. Let me thank you, all of you who have remained till the end, for coming to the school, for your questions, for everything. And obviously, if you guys have more questions, doubts, or you want to discuss, comment about these perspectives, I think we are very happy. There's a bunch of us here connected as well, not only just myself, and we'll be very happy to discuss with you or solve some final doubts you may have before we call the end of the school. Thank you very much, guys. Thanks a lot. I stopped sharing, and then I managed to see the screen. Yeah. Thank you, guys. Okay, I see some questions. You can unmute yourself.
Okay, hi. So yeah, I got a bit curious when you mentioned magnetic hydrodynamics and fluid mechanics. So are you planning to couple basically the scalar fields and all the fields to the plasma, and how are you planning to implement?
Well, I mean, we are far away from having you know, something useful, but we are planning to follow same kind of prescriptions in the pencil code. And at the same time, the whole field theory sector, we already have it implemented.
Yes.
So the coupling we are planning between the two sectors is going to be in a first approximation following the effective interaction, like the one implemented in the works of Heidmarsh and David Weir et al. But of course, there are going to be, you know, other circumstances that we may want to consider, you know. So we are very open to think at this point what kind of approach we want to take.
I see. But at least as a kind of starting point, you're thinking about basing this on basically the prescription in pencil code.
Yeah, absolutely. Because, you know, the good thing of pencil code is that it's been worked out by a lot of people over many years. It's a very solid code. And then it's already given a lot of prescriptions about how to do fluid dynamics. So one should never reinvent the wheel from scratch when the wheel has been already invented, you know.
Right.
We are learning from them, and we are in association actually with people who are experts on the topic. And the idea is that we will create our own module on fluid dynamics coupled to field theory. Yeah.
But is there a way you can already kind of implement the Fortran? So pencil code is written in Fortran.
Yeah.
So would you have to translate that into C++, or could you somehow communicate?
We will write our own kernels, to do the fluid dynamics in our language. Of course, yeah. It's gonna take some effort. But
I understand.
On the other hand, what is the major difficulty typically when you want to deal with a new theory or a new framework is how to discretize correctly your theory. Once you know that, the prescription, then translate it into the computer is a matter of from days to weeks, but nothing special.
Yeah.
Okay, and that's the thing. We are trying to learn very well all the different limits, approaches, circumstances under which you want to do it in the full generality, and then we will translate it into our language in CosmoLattice. Yeah, and of course your Hicksless idea is something I already have in mind as well.
Yeah. But exciting times. I look forward to these developments.
Okay, it'll take time though. It's one of the how to say corners of the code that is gonna take some time because it requires a lot of development, but it'll be there. It'll be there sooner or later.
Okay. Cool.
Yeah. Thank you. Okay, cool. Thanks for your comment. Mohammad Hossein saying thanks to the organizers and that this will be a well-explained tutorial for the future use. Well, we hope so. No, I mean, it's going to remain there in YouTube and you're going to have always the slides available in Indico, in the schedule of the website. So sure, you're going to have plenty of material to come back. Although my recommendation really is that if you have attended the school with the intention of really learning about this, is that you jump into the manual, because then you're going to discover that most of manual and the review, most of the things we are telling you, by presentation, they are explained there in full detail, and hopefully with certain pedagogy, that you can really follow all the details from scratch, essentially. Yeah.
Very difficult for me to anticipate that. Sorry,
is that a question, David?
No question. Oh. I'm happy to learn and study this seminar, but I don't have the basics, fundamental notion to this kind of school. But I will try to do my best because I have my thesis in mathematical physics, but try to the conformal field theory and the integrable systems. So I will need to convert with in cosmological story or astrophysical story. So I don't have possibility to contact someone who can help me in this new orientation.
Okay, sure. Well, now you know who we are. Good.
The next section is which?
Sorry?
The next section or this school?
The next section, what do you mean, sir? The next edition of the school, you mean?
Yeah, the next edition, yes.
Well, it will be next year. Details to be determined, but it's gonna be in person, very likely. Yeah.
Okay.
Because I think we lose, the interface with the people locally. We don't see your faces. We don't know if you are following. We don't know if you are compiling well. We don't know if you are getting the right output. And it's much better for us, and I think for the students actually to really be in person, so we can really guide you much better. Details to be decided next year. Yeah.
Okay.
On the other hand, we are gonna repeat pretty much the same concepts. So if you have attended the school and you see the videos, I'm not sure there will be much of any point for you to attend the school anymore, because at least for next year we are going to repeat the concepts. Next year will be the 3rd edition of the school. If I start feeling that there is a emerging community of young people like yourselves that are catching up and building up in this expertise, then we will start offering at some point an advanced school, an advanced technique school, you know, but this to be decided in the future.
Okay, that's good. I will be happy to participate in person at the next edition.
Excellent, David. Thank you.
Okay.
Tucker has a comment. Yeah, many things to you. Yeah. Hopefully, having this online will help of those of you who really want to go deeper inside. And yeah, thanks for coming, and especially to Tucker and other American people that for them is very, very early in the morning, and yet they made the effort in the middle of the night, in the middle of their nights to join us online. You know.
All right.
Okay, someone else wants to say something? Yeah, Jan. Yes, please go ahead.
Yes, I have a comment. In CosmoLattice, when you calculate the spatial derivative, you use the neighbor points in the final differentiation to calculate the spatial derivative. And I know that there is a more accurate method called the spectral method that use the global points to fitting the derivative. Have you ever think about that?
Yeah, the problem of the spectral method is that if you solve, there are a couple of codes actually publicly available, which solve the equations in Fourier space, and then you can do your equations in a different manner, and it might be more accurate for spatial gradients. However, it's extremely costly, you know. So when I've learned about these techniques, I was never convinced that they could overtake the power that solving in real space you can do. So if you are worried about the accuracy of gradients, you can always call a higher order gradient implementation. CosmoLattice does not just rely on a given first neighbor thing. CosmoLattice gives you some basic implementation where we use that, but you can essentially implement whichever you want in your kernel, you know, and you have all the language to do it. And you can do higher order Laplacians, you know, that's not a problem at all. It's actually a relatively trivial exercise to implement in CosmoLattice. The problem of doing it like that is that if you are higher order in lattice spacing, since these are wave-like equations, you need to be proportionally higher order in time evolution. So if you implement a Laplacian that is as good as flow into the continuum to order 4 or 6 in the lattice spacing, you need the equivalent accuracy in the time step, which means you need to use one of the higher order integrators we have, which implies it's going to run much slower, your dynamics, significantly much slower. So it's only depending on whether you have a need to resolve your spatial local coordinates in a more refined manner than what is standardly done by everybody, whether you want to go in that direction you are asking about.
Yes, I'm interested in try that method, but the CosmoLattice is too complex, so I still need to have the try.
Yeah, my recommendation. I mean, I agree with you, Ji Yang, that CosmoLattice, you know, we had two goals in mind when we started thinking of it, Paco and I originally, then with Wessel, then with Adrian. The first goal was we want to make a very powerful and versatile code. And I think that we have managed. You know, it's extremely powerful. It's very well parallelized thanks to Wessel and Adrian. It scales very well in clusters, you know, the parallelization scales very, very well. And it's very powerful in that respect and very versatile because it already has interactions of many kinds. And next year, once we make available the branches for action interactions, for non-minimal gravitational interactions, for cosmic defect networks, possible for non-minimal kinetic terms, etc. It's going to even have more, okay? However, the price we have paid is that it has become a very complex code. And I understand it is overwhelming the first time when you have to deal with it, and you may want to cut corners, you know, and skip the details inside the code. The problem of doing that is the same as when you are learning string theory or quantum field theory. If you want to master the discipline, you have to learn it from scratch, and you cannot skip the details. And here is the same, you know. This is a complex code because this is complex phenomena at the end of the day that we are covering in full generality. And if you really want to be able to do things like what we've shown you, like for instance, action inflation today, or something else that you have in mind, you need to go inside the code with patience and time, okay? Which, if you are a PhD student, this is the ideal moment in your life to do. If you are a senior postdoc, probably you are not having as much time to do this anymore. So it's really up to you.
Okay, okay. Thanks for your advice. Thank you.
My pleasure. Okay, any other comment, observation, discussion, criticism, whatever, you know, guys? Suggestion, you know? Well, if not, then let me thank you all again for joining us till the last day. It's been an intense week. You know, 5 days lectures is not short. It was also intense for us to prepare this, to organize this, to make sure everything goes in place. So thank you very much for joining us, for the effort. And since you have the slides and the videos available online, don't hesitate if you have basic doubts. But my recommendation, please, once again, is that if you do have these doubts, first check that in the manual this is not resolved, you know, that this is not explained, because probably it's fully explained in detail there, most of your doubts, you know. Anyways, thanks a lot. And now I think we can call the day and the week. Take care and all the best in your careers. Ciao, ciao.
Thank you.
Thank you, guys.
Thank you very much.
My pleasure.
Thank you very much.
Guys.
Thank you very much. Next time.